Welcome to the Breakthrough Broadcast, a podcast about innovative STEM solutions to real-world problems. From emerging technologies to practical research, Drew Reck explores how science, engineering, and bold thinking are shaping the future.
I'm Drew, and today's episode is about a technology that lets you suspend objects in midair, using nothing more than sound. It's called acoustic levitation, and at first glance, it feels like a magic trick. Small clusters of particles, a small bead of plastic, or even a small droplet of water can float, perfectly balanced, with no strings, no magnets, no hidden supports. Just carefully arranged sound waves holding it in place. Sound usually feels intangible. We hear it, we feel it vibrate through the air, but it's easy to forget that sound is a physical force. Every note, every noise, every vibration pushes on the world around it. Most of the time, that push is too weak or too scattered to notice. But under the right conditions, sound can become powerful and precise. Acoustic levitation takes advantage of this, using sound to create stable pockets in space where objects can rest, seemingly defying gravity. The visuals are striking. Tiny droplets hover as though frozen through time. Lightweight materials bounce and spin in ways that almost look choreographed. Scientists can even merge droplets together midair, or move them along an invisible path created by sound waves. These demonstrations aren't just flashy tricks for labs. They reveal the hidden structure of sound itself, and open up a space where physics feels tangible, playful, and even alive. There's also a serious side to all this. Acoustic levitation is more than just an entertaining curiosity. Researchers are investigating its use in drug delivery, where delicate medicines can be handled without contamination. In manufacturing, sound could help position and assemble components without physical contact. In space exploration, it could offer ways to manipulate liquids in zero gravity, where containers don't have to behave the way we'd expect. By taking something as familiar as sound and applying it in unexpected ways, scientists are unlocking possibilities that range from futuristic healthcare to new industrial techniques. In this episode, we'll look at what makes acoustic levitation work, the physics behind how sound creates invisible scaffolding, and why this area of research is both fun to explore and deeply important for the future. The story of sound, as more than just a vibration in the air, is a reminder that even the most ordinary forces around us can be reimagined into extraordinary tools. To understand how acoustic levitation works, we need to start with the basics of sound itself. Sound is simply a vibration traveling through a medium, usually air. When something vibrates, a speaker cone, a guitar string, or even your vocal cords, it pushes on the air around it, creating alternating regions of high and low pressure. These regions move outward in waves, like ripples on a pond, but instead of water moving up and down, the air molecules are compressed and stretched along the direction the wave is traveling. This type of wave is called a longitudinal wave. What makes sound powerful is that these compressions and rarefactions are physical. The molecules in the air actually shift back and forth, colliding with each other and passing energy along. Normally, that push is tiny, which is why we can yell as loud as we want without knocking anything over. But if you scale up the precision and intensity, those pushes can become strong enough to interact with matter in surprising ways. Acoustic levitation relies on this idea by taking sound waves and arranging them very carefully. The key is interference. When two sound waves meet, they can either add together or cancel each other out. If the peaks and troughs line up, they reinforce each other, creating a stronger wave. If they're opposite, they cancel. Place two sound sources facing each other, and you get a standing wave. A wave that seems like it has points that are not moving at all, where the sum of the two waves is always a constant. But reality, it's just the sum of the two that are facing opposite directions. In standing waves, these stable points, where nothing seems to be moving, are called nodes, where the air doesn't shift much. There are also antinodes in standing waves, where the air moves the most. These nodes and antinodes form an invisible pattern in space, almost like a 3D lattice made out of pressure. And here's the crucial insight. If you put a small object into that pattern, in the right places, the sound waves push on it from all directions. Place it just the right spot, and those push-ins all balance out, holding the object steady. It's a little like balancing a ping pong ball in a stream of air from a hairdryer. The ball doesn't fall because the moving air creates a stable pocket that keeps it in place. Acoustic levitation is the same principle, but instead of a stream of air, It's a stream of sound sculpted into a precise shape. One important detail for this process is frequency. Higher frequency sound waves have shorter wavelengths, which means the standing wave pattern can hold smaller objects more tightly. Ultrasound, which is sound above the range of human hearing, is often used because it allows fine control and avoids being painfully loud to anyone not nearby. Another detail is intensity. To levitate even a lightweight droplet, the sound waves need to be strong enough to counteract gravity. That requires carefully tuned speakers that can generate high sound pressures without breaking apart the wave pattern. If the setup drifts, even slightly out of alignment, the object falls and the system fails. When researchers demonstrate acoustic levitation, they're showing us sound not as something abstract, but as something with structure. The air itself becomes an active player, shaped into a scaffold that can cradle matter. What's usually invisible, sound waves, suddenly takes on a form and strength, turning vibration into movement and stability. And this is why acoustic levitation is so compelling. It takes something we normally experience as fleeting and reveals its hidden solidity. Physics becomes visible, touchable, as droplets hover and beads float in midair. Acoustic levitation grabs people's attention because it flips our expectations. We're used to thinking of sound as something fleeting. Here for a moment, gone the next. It fills a room, then disappears without leaving a trace. But in these experiments, sound takes on substance. It becomes something that you can see working in real time, almost like sculpting the air into invisible hands that can hold and move matter. There's a kind of childlike wonder built into seeing droplets or beads hover without any visible support. The effect feels like magic, even if you know the physics. Watching a bead float and then shift as the sound field is adjusted makes the sound feel alive, as though the vibrations themselves are reaching out to interact with the world. This sense of play is what makes acoustic levitation so capturing outside the lab. It's a reminder that science can surprise us in ways that feel almost whimsical. The demonstrations themselves almost look like science fiction scenes. Droplets of liquid can hover side by side, then merge together midair without ever touching a surface. Lightweight materials bounce in patterns that look choreographed, like they're dancing to music we can't hear. Some researchers even arrange sound fields so objects follow a path, gliding along as though guided by invisible tracks. And it's not just about what you see, it's also about how this challenges our intuition. We're so accustomed to gravity being absolute that seeing an everyday force like sound balance it out feels deeply strange. It reminds us that the universe is full of interactions we rarely notice, and that even something as familiar as sound still has secrets to reveal. Part of the fascination comes from accessibility as well. Unlike other advanced physics demonstrations that require enormous particle accelerators or billion-dollar telescopes, acoustic levitation can be done on a tabletop. Some experiments even use relatively inexpensive ultrasonic transducers, which, despite sounding scary, can be bought on Amazon. This isn't just a phenomenon locked away in big research labs. It's something that hobbyists and educators can recreate. Seeing levitation in the classroom, or even at home, makes the physics feel personal and approachable. Ultimately, the fun of acoustic levitation is that it blurs the line between science and spectacle. It's a tool, but it's also a performance, showing us the physics in action in a way that anyone can appreciate. That mixture of playfulness and depth is part of why researchers continue to explore it, not only for what it can do, but because it reveals how much potential still hides in the forces we take for granted. While acoustic levitation is fun to watch at a science museum, its potential reaches far beyond classrooms and demonstrations. In fact, some of the most serious and promising research involves medicine, pharmaceuticals, and even space exploration. The same forces that can levitate a styrofoam ball might one day help save lives or enable missions to other planets. Let's start with medicine. One of the biggest challenges in drug development is handling delicate materials without contamination. Many modern drugs are based on proteins or other fragile molecules that can be damaged when they touch a surface. Imagine trying to study a protein while it's sitting on glass or metal. The surface of this glass or metal can alter the protein's structure. This is a major roadblock for researchers trying to design treatments at the molecular level. Acoustic levitation provides a unique solution, handling substances without containers or surfaces. When a droplet of liquid is suspended in midair by sound, it never has to touch a solid surface. Researchers can study how proteins fold, how crystals form, or how drugs behave in a truly untouched environment. This could accelerate the process of designing new medicines by giving scientists a clearer, more accurate look at the molecules involved. Drug delivery is another exciting frontier. Certain experimental systems are exploring how acoustic waves could guide medication through the body. For instance, focused sound fields could help target specific areas, moving drug particles to the right spot without invasive surgery. While this research is still in early stages, it suggests a future where doctors might use sound as a kind of invisible hand to move treatments exactly where they're needed. The appeal is obvious: fewer side effects, lower doses, and more precise treatments. Now we can move even to outer space, where acoustic levitation could make an enormous difference. In microgravity, handling fluids and particles is notoriously difficult. Liquids don't sit neatly in containers. They form floating blobs that can be messy and hazardous. This poses challenges for anything from conducting experiments on the ISS to preparing food and medicine in orbit. Acoustic levitation could provide a way to manipulate materials without relying on gravity or physical tools. NASA and other space agencies are interested in how sound fields could help astronauts manage experiments in space more effectively. For example, scientists could crystallize proteins in microgravity while keeping them completely suspended, avoiding contamination and gaining insights into their structure. Acoustic manipulation might also be used to build or assemble materials in orbit, where traditional tools don't behave the same way. Beyond research, there are even potential uses in spacecraft design. Acoustic waves could help move small particles of fuel or coolant in systems where pumps would be heavy or impractical. And because levitation works without contact, it reduces the risk of wear and tear, making it attractive for long-duration missions. Another serious application lies in manufacturing advanced materials. Acoustic levitation can be used to create perfectly uniform droplets, or to mix substances in ways that are difficult with containers. This could lead to high-precision materials with unique properties for electronics, medicine, or engineering. Researchers are already exploring how to use acoustic levitation to study alloys, nanoparticles, and other complex systems where precision is key. Even with its fascinating applications, acoustic levitation faces significant limitations the researchers must overcome before it becomes widely practical. While levitating a droplet or small bead in a lab looks effortless, achieving precise control at large scales, or with more complex materials, is far from simple. One major challenge is size and weight. Current acoustic levitation setups are generally limited to tiny, lightweight objects. The strength of the sound waves required to counteract gravity increases rapidly with the mass of the object. Levitate a droplet of water or a small plastic sphere, and the setup works well. Levitate a larger object, and the system quickly reaches the limits of what the transducers can produce. This makes scaling up the technology for industrial or consumer applications a difficult hurdle. Another limitation is stability. Acoustic levitation relies on extremely precise arrangements of sound waves. Small deviations in frequency, alignment, or amplitude can destabilize the levitated object, causing it to fall. Environmental factors, like air currents or temperature fluctuations, can also interfere. Maintaining the exact conditions needed for stable levitation over long periods is a non-trivial engineering issue. Energy and equipment requirements pose additional challenges. Ultrasound transducers must generate very high sound pressures, often requiring specialized electronics and careful calibration. The cost and complexity of these systems currently limit their widespread adoption outside research labs. Material constraints are also significant. While small droplets, beads, and foam particles work well, denser or more irregularly shaped materials are much harder to levitate. Researchers are investigating solutions like phased arrays of transducers and hybrid techniques combining acoustic fields with magnetic or optical manipulation. But these methods add further complexity. Finally, there are limitations in all of the application-specific contexts. Drug delivery using acoustic levitation is promising in concept, but delivering precise doses safely in a living organism requires overcoming biological and mechanical constraints. Similarly, using the tech in space or industrial environments demands robust, automated systems, capable of operating reliably without constant human intervention. Despite these challenges, acoustic levitation continues to attract attention because the potential benefits are so compelling. Researchers are steadily developing better transducers, smarter control algorithms, and hybrid methods to expand the range of materials and scales that can be levitated. These innovations may gradually overcome the current hurdles, moving the technology from a lab curiosity to a practical tool in medicine, manufacturing, and space exploration. Acoustic levitation is a reminder that even a seemingly magical technology has limits. Understanding those limits is not a reason to dismiss it, but a guide for where innovation is needed. Each obstacle highlights both the ingenuity of current solutions and the exciting work still ahead in turning sound into a tool that can manipulate the physical world in unprecedented ways. Acoustic levitation shows us that even the most familiar forces in our world, like sound, can behave in ways that feel astonishing. What starts as a simple curiosity, like making a droplet hover in midair, opens the door to deeper insights about physics, engineering, and the potential of human innovation. Sound, usually thought of as something we hear or feel, becomes a tangible tool capable of holding, moving, and even manipulating matter. That shift in perspective is both fun and profound, showing how science can transform the ordinary into something that's extraordinary. The beauty of acoustic levitation lies not in the visuals, but in the science it reveals. Understanding standing waves, nodes, antinodes, and how sound interacts with matter gives us a glimpse into the invisible architecture that shapes our universe. Watching small objects float is more than just a trick. It is seeing physics in action. It's playful, engaging, and deeply educational, reminding us that discovery often begins with curiosity and wonder. At the same time, acoustic levitation has serious implications. From handling delicate drugs without contamination to guiding experimental materials in space, the technology could transform medicine, research, and engineering. Scientists are exploring ways to harness sound for drug delivery, to assemble materials without containers, and to conduct experiments in microgravity environments where traditional tools fail. These applications demonstrate that a technology that looks like a spectacle today could become a tool for solving real-world problems tomorrow. Of course, there are limits. Again, scaling the technology to larger objects, maintaining stability, and creating practical, energy-efficient systems remain large challenges. But understanding these challenges is part of the story. Each obstacle highlights where innovation is required and where creativity can push the boundaries of what's possible. The combination of fun, science, and potential makes acoustic levitation a rare example of a technology that excites both the imagination and the practical mind. In the end, acoustic levitation reminds us that science is not confined to laboratories or textbooks. It can be playful, surprising, and beautiful, while also holding the power to change the way we live and work. What seems like a floating bead or droplet today could be part of life-saving medicine, futuristic manufacturing, or even space exploration tomorrow. By learning to harness the hidden power of sound, researchers are showing us that the boundaries of possibility are far wider than we may have originally imagined.
Thanks for tuning in to the Breakthrough broadcast. If today's conversation sparked a new idea, share the episode and follow the show wherever you listen. Got a question, idea, or breakthrough of your own? Reach out at breakthroughbroadcastconnect@gmail.com. Until next time, keep questioning, keep building, and don't wait for the future. Help create it.